a2 of x squared plus x to the fifth equals 0. You can always scale the highest coefficient to equal 1. So we remove the x cubed and the x to the fourth. Okay? And this can be solved using, using hypergeometric series, but also using Fuss-Catalan numbers. Then there's something called the Bring-Gerard normal form. And that is very simple. That is x to the 5 plus from minus x plus gamma equals 0. And it may surprise you, but the general quintic can always be reduced to this form. And this is even easier to solve. Here, the coefficients of x squared, x cubed, and x to the fourth have all been removed. And so there is this. But that's not the end of it. There is also something called the Brioche normal form. And that looks like this. X to the fifth minus 10c of x cubed plus 45 c squared of x minus c squared equals 0. And I don't know why there are all these different normal forms. But anyway, all of these can be solved using the Fuss-Catalan series. And then domains of convergence can be figured out for these solutions. And also, it's not just that the combinatorics people prove all these theorems and don't reference each other. They don't even seem to know that people who work on complex analysis have derived these results and proved some of these theorems. And the people who work on complex analysis make no reference at all to the combinatorics. So I wrote this whole collection of papers, and they all derive these functions, prove these theorems, prove these identities. Nobody references anybody else. And
You do.
And I do, yes, and nobody cares. Yes, that's true. All right, fine. We got that far. What's the time? Oh, very good. Okay, now I'm going to talk about the applications to combinatorics. So I told you there are all these different applications. Well, I guess I want this plot. So all right, for the rest of my talk, I'm going to talk about applications to combinatorics. And Stanley has zillions of applications, and it seems to me that for every application of Catalan numbers, there's a generalization to Fuss-Catalan numbers. And so I said to Zylberger that, you know, I'll just keep on talking and cut it off whenever it reaches the end. But I think, because there's just an infinite number, or a very large number of these. But no, I'll give you 3 applications, okay? We'll start with the Catalan numbers, okay, and say, all right, we might be able to do it like this. 1, 2, and 3. 3, 2, and 1. Triangulations of convex polygons. If you have a convex polygon, in how many ways can you partition it or dissect it into triangles that don't overlap with each other? I think that's reasonably obvious to understand what that means. And the number of ways of doing that, if the number of vertices is n plus 2, then the answer is C of n, which is just 1 of 2n plus 1. 2n plus 1n. And that's the number of ways of doing it. Okay. The obvious question then is, suppose we want to dissect it into quadrilaterals or pentagons. Oh, something else. For the purposes of dissection, a convex polygon is equivalent to just points on a circle. You can always shift the points out or move them in until here. So some people prove theorems for dissections of points on a circle, and other people, they write papers and they talk about convex polygons. As far as dissections are concerned, it's the same thing, it's equivalent. Okay, now with any convex polygon, with any number of vertices, well, greater than or equal to 3, you can always dissect it, partition it into triangles. But it's obvious that with a pentagon, you can't partition that into quadrilaterals. So there's some restriction on what the number of vertices can be. All right, so let's go with Kim 2008. And the theorem is that we have the number of vertices is n of k minus 1 plus 2. That's the number of vertices in the polygon. And that's how you can partition that into k plus 1 gods. With n of them. And you notice here that if I put k, to get triangles, I would put k equal to 2. 2 minus 1 is 1, and that is just n plus 2. It's just n plus 2, and n can be anything. But if I put k equal to 3 for quadrilaterals, then this will be 2, and this will be 2n plus 2. So, as I said, n then cannot just be 5, it has to be an even number. So, this, and the number of ways of doing that, he showed, is given by this number of c, which is 1 over n, nk minus 1, n minus 1. And this, it's explained in the handout, it's derived is just an of k1. Okay? This Fuss-Catalan number with k is here. But you notice Kim's definition. And this is what I mean by the example of an unnecessarily restricted definition. That he's defined this just to solve his problem, and it's very limited. It won't solve any other problem. This, on the other hand, will apply, this definition will apply to many other problems, and with these parameter values, it gives the solution to you. I guess my gun won't work out so well. Yes. Okay, let's go to Chu 1987. And Chu proved a more general result. All right, so we can partition this into k plus 1 gods. Let's partition it into V1 polygons with V1 vertices, N1 polygons with V1 vertices, and N2 polygons with V2 vertices, and N3 polygons with V3 vertices, and so on and so on and so on. So the number of polygons, the number of points is then the sum of Ni of Vi, okay? And the number of ways of doing that is given by this vector, and so this is a sum up to k is given by 1 over n dot v plus 1 of n dot v plus 1. And then over here is n1 and n2 and n3 and da da da. And this, in terms of my definition, is just A of n vector of v vector, and again r equals 1. Now you notice Chu proved a more general result in 1987, because here it can be n1 polygons with v1 vertices and n2 and so on. But this is 1987, and this is 2008, and this is what I mean, that nobody seems to go back and search if somebody else has already proved. In 1987, he proved a more general result than this thing from 2008, but that just seems to be the way in this business.
No. Did you email Kim to tell him that he was scooped by Chu?
No. No, I didn't do that. I did contact, there were some excellent papers written by a person called Ling from the National University of Singapore. But when I contacted the Singapore University Mathematics Department, the chairman told me Professor Ling retired a long time ago, and we no longer have contact information for him. Because he wrote excellent papers, and I wanted to get in touch with him. But he published his papers in the 1970s and 80s, and I don't even know if he's still alive. The university itself has no contact information for him. Now, what's the use? Dear Professor Kim, I read your paper, and the result was published by somebody else before you. So, what do you mean? All right, but anyway, that's dissections of polygons or points on a circle. Chu proved his theorem for points on a circle. Kim proved his theorem for polygons. But now, let's talk
But you should write down. Did you write down in the survey? Did you point it out?
To whom?
Did you write the paper? Are you going to write up this, or you already wrote up this?
Well, I wrote up some and I sent you, but...
I know, but
this is
the
not-
fact that true prove special, that Kim prove a special case of true, is it pointed out in writing for historical?
Not in the manuscript that I showed
Yeah,
you.
so it should be for record.
It can be rewritten, yes, that also. All right, now let's talk about rooted trees. We're actually going to talk about complete rooted trees. That means that a K array rooted tree means that every node has either K children or 0 children. It has to be all or nothing. A binary rooted tree will look something like this. It will have 2 children, and then this one may also have 2 children, but this one may have 0 children, and then this one may have 2 children. But it either has 0 or it has the maximum number. So if it's K equals 3, then it will be 3 children, and so then this one will have to have 3 children, and then this one may have 3 children, and this one may have 3 children, and this one may have 2 children. It either has 3 or 0. Anyway, in the case of K equals 2, the number of binary rooted trees with n nodes is given by the Catalan number C of n. And in the case where, so again, this is 1 over 2n plus 1, 2n plus 1n. And in the case where we replace 2 by k, then this is just kn plus 1. This is just kn plus 1. And the answer is just an of k1 again. And so that will give the answer for k equals 3 or k equals 4. That's what I mean when I say that any application which has a solution of a combinatorial problem with Catalan numbers, there's a generalization to Fuss-Catalan numbers. All right, now the third and the last one is called drift paths. Suppose we have like a random walk. We start at 0 and we can go up or go down, or we can go up, down. But it always has to stay on or above. Let's call this x and let's call this time t. It always has to stay above, or it cannot go below this line. Now it's obvious that the number of up steps and the number of down steps must be equal. Suppose there are n steps, then the number of dict paths of length 2n is again equal to cn. That's a Catalan number. Now it's actually better to rewrite this in the following form. Here is t, here is x, here is the line t equals x. And to say it starts like this and goes like this, and it ends at the point n. Okay? And this is equivalent. The number of paths is the same. But this can be generalized. Think of the horizontal axis as time. The vertical axis we can generalize to x1, x2, x3, and so on. We can have multiple, and the slope doesn't have to be 1 to 1. The number of paths that start from the origin and do not cross this hyperplane, which is the hyperplane in the theorem is called as x0 equals the sum of mu I times xi plus, and it doesn't have to end at that point, it can end somewhere over here, some distance, which is alpha. That number is, that was proved in 1975, and the answer for that by Chernyenko and Moanty is given, and they used alpha. So, okay, alpha over alpha plus the sum of mu I plus 1 of mi, and then it's the same thing, alpha plus sum of mu I plus 1 of mi, and then this is just n1, n2, nk. And this is equal to A with the vector n of mu plus the vector 1. The vector 1 means this 1, 0, 0, 0, or 0, 1, 0, 0, whatever. And alpha. So instead of r, they use alpha. And this is a generalization of Catalan numbers to multi-parameter. See, all of these were just generalization to single parameter Fuss-Catalan numbers. But that is an actual generalization, combinatorial generalization, where there can be multiple space dimensions. It doesn't have to be just a one-dimensional random walk with one space and one time. It can be multiple space and one time. And that is the generalization. That's exactly like what it is, and I reached the last slide. So that's very good.
Thank you very much. Sateesh will be glad to answer questions in private. If you'd like to join us for dinner, please let me know right now. It's Evelyn 6:45.